So we have seen earlier that the goal of the expectation maximization algorithm is to find the maximal likelihood solutions, where we can express this as the argmax over the unknown parameter of the log likelihood distribution, which is given by P of x conditioned upon theta, for some models having latent random variables, and this would lead to the expression becoming the argmax over theta and the log over the marginalization of these latent random variables, which we denote as z, and the joint over the joint distribution of x and z conditioned upon theta. And we saw that because this summation or this marginalization over the latent random variables appears inside the log term, so this results in the solution not in closed form. This means that we have to come up with an iterative method to solve this particular problem, or this particular maximization problem, and we call that the expectation maximization algorithm. And we also saw that in the earlier case that we derive the solution for a Gaussian mixture model. What this means is that the conditional probability or the likelihood probability of x conditioned upon z and theta, it's actually given by a normal distribution, which we denote as mu and sigma, a set of mu and sigmas, and as well as the categorical distribution over our latent random variables, which is z conditioned upon, to be more specific, it's actually pi over here, which is given by the categorical distribution. We'll now look at the case of the derivation of the expectation maximization algorithm for a general distribution, for a general mixture distribution, which need not necessarily be a mixture of normal distribution or mixture of Gaussian distribution. We will generalize this to be any distribution, a mixture of any distribution. So now let's start by looking at the log likelihood function in general, where we have seen actually earlier that the log likelihood function can be rewritten into this form, which involves the marginalization over z. So in this case over here, the marginalization is written as a summation because z here is a latent random variable that is discrete. It's an assignment which actually takes either 0 or 1 that we have seen. So that's why it's a summation. But in the general form, this could also be a continuous random variable or continuous latent random variable, which could also end up to be integral of z, which means that the categorical distribution here need not be a categorical distribution. So here in the discrete form, this would be a categorical distribution. But in this continuous random variable form, it could actually be a normal distribution instead of a categorical distribution. And here we'll follow the same notation where x is the set of all the observed random variables and z is the set of all the latent random variables. Theta would be our unknown model parameters or the distribution parameters that we wish to find. And regardless of the latent random variable being discrete or continuous, a key observation remains is that the summation or integration appears inside the log term. So this summation term here, it appears inside the log term, and the integration over here also appears inside the log term. And this means that the marginal probability doesn't simplify even when the joint probability belongs to an exponential family. So we have, if you recall from lecture 6, that the partial differentiation, it's enough for every parameter since over the log likelihood, since this is assumed to be IID. That means that the sufficient statistics would be enough for us to find that particular unknown parameter. But in this case, as we have proven earlier, that the end result of the partial differentiation leads to a coupled solution. This means that all the parameters are coupled together, and we would have no closed form expression for the maximal likelihood solution. And so in the general EM algorithm, let's also define the complete data and the incomplete data, which is actually what we have already seen in the Gaussian mixture model. But now let's define it in a more general form. So the complete data simply means that both the observation and the latent random variable are known. This would become this would become an easy problem to solve because we already know the assignment. That means that each one of these observation here, we know which cluster or which assignment of the Z that is going to be assigned to in the clustering problem. So that's for the discrete case. And we also look at the incomplete data definition. So in this case here, the observation is known. So all the X are known, and the latent random variable Z, which is the assignment latent parameter, or the latent random variable, it's not known. So here we do not know, for each point we do not know which class it's assigned to. And here, in order to solve for the unknown parameters as well as the latent random variable, we'll end up with a chicken and egg problem that we can only solve using the alternating solution. So it's straightforward to maximize the likelihood function for the complete data set, because in that case we would have known Z, and we simply treat all this as our observed random variable. So this means that the log term would there won't be a summation that appears inside the log term. All we need to do would be to just sum over the we'll just sum over the log of the likelihood of Z and theta, and this would be easy to solve. It's similar to what we have seen in the lecture 6. So in practice, however, unfortunately, we are not given the complete data. This means that we are only given the observations of data of X, but we are not given the assignment or the latent random variable here. So Z here is unknown, or it's actually a latent random variable. So since we have the incomplete data, we'll instead consider the maximization of the expected value of the complete log likelihood in this with respect to the posterior distribution of our latent random variable. And we'll see that by doing so, we'll be able to derive the general expectation maximization algorithm. So this strategy over here, to take the argmax of the unknown variable over the expected value of P of Z conditional upon theta and X over the log likelihoods, over the complete log likelihood of X and Z theta over here. We'll see that by doing this, we'll actually avoid the situation where we need to have a log term where the summation is over Z is inside the log term, where we can see that this end up with a non-closed form solution. So we'll see that by doing this, by optimizing over this form over here, it will lead to the alternating strategy in the EM, or in the expectation maximization algorithm. Now, in the expectation step, we'll still do the same thing, that we'll initialize we'll use the initialized value of theta, or the parameters from the previous step, or we call it the current parameters, or theta O, to find the posterior distribution of the latent variables. So this will find this guy over here, which is actually our responsibility that we have defined earlier on. But now we are going to call this term here simply the posterior distribution over the latent random variable in a more general way. Then we will then use this posterior distribution to find the expectation of the complete data log likelihood, evaluated for some general values of theta. And here, this expectation, we will denote it as Q theta and Q and theta O is given by this guy over here, this expectation term over here, which I have written in the previous slide. So instead of that means that instead of just looking at the log likelihood term, which is given by the log of px conditional upon theta, we are going to look at the expectation or the expected value of the complete log likelihood under the posterior distribution of our latent random variable z, given that it's conditioned upon some O parameters from the previous step. So notice that this is evaluated from the parameters in the previous step, and this is under a general form of data, a general form of the parameters, which we will then optimize in the maximization step. And this can be written into this shorthand form over here, expectation over the posterior over the complete log likelihood. And so in the maximization step, we'll simply revise the parameter by simply maximizing over the unknown parameters on the Q function that we have evaluated in the earlier expectation step. And this gives rise to this formulation over here. And we can see that, interestingly, now the summation over z over our latent random variable appears outside the log. And so the objective of the general EM algorithm can be summarized as given a joint probability distribution of x and z conditional upon theta over the observed random variable. So x here is actually our observed random variable, and z here is our latent random variable, which means that we are not observing it, and governed by a set of unknown parameters. So these are unknown parameters. The objective of the general EM algorithm is to maximize the log likelihood function with respect to theta. This means that we want to do an argmax of this log likelihood function with respect to theta. And we have seen in the earlier slide that we can do this using the general EM algorithm by choosing an initial setting for the parameters, which we call theta O. And in the expectation step, we simply first evaluate these terms here. And this is the posterior distribution. And after we have evaluated the posterior distribution over the latent random variable, we will evaluate this term here, the Q function here, which is given by the expectation over the complete log likelihood on the posterior distribution of the latent random variable p of z conditional upon x theta O. And we'll simply do a maximization over the unknown parameters on Q in the maximization step. And here we can see that the log term appears to be inside of the summation. We'll do this iteratively, and once we have checked that the theta over here, the unknown parameters, is no longer changing, this means that it has converged, we'll terminate the EM algorithm. So this is called the general EM algorithm, because notice here that we are not assigning any specific distribution to the posterior distribution of the latent random variable, as well as we are not assigning any specific distribution to the joint distribution here, in comparison to the previous case where we have looked at the GMM, where here this guy over here is a categorical distribution, and this guy here can be evaluated into x conditional upon z and theta, which is our normal distribution in that particular case. Now, there is a interesting problem that might occur in the expectation maximization algorithm, which we call the singularity problem. And this is the problem where a Gaussian or any distribution in general can get erroneously fitted to one single data point. So in the case of a Gaussian distribution, this might mean that it becomes a point function over here, where the sigma, the distribution of the variance, becomes 0, it approaches 0. And this is what we want to avoid, or what we call the singularity problem that we want to avoid. So in this case, we can actually alleviate the problem by applying a maxima a posterior on this Q function. So instead of the expectation over the expectation over the posterior distribution, x and theta, on the complete log likelihood data here, we're going to add a regularization term on the prior, which is on the unknown parameters, which is written as log of p theta over here. And by optimizing this over the prior, where we can assign a Dirichlet prior on the mixing coefficient, as well as an normal inverse Gaussian distribution on the mu and sigmas in the case of the Gaussian mixture model, to regularize the data, to prevent the distribution from collapsing into a singularity point like this. And in that case, we will simply assign some probability to the normalized inverse Gaussian such that sigma will not go to 0. Now let us revisit the derivation of the EM algorithm on the Gaussian mixture model. The complete data log likelihood is now given by this term over here, where which is what we have seen in the earlier slides, the log joint probability of x and z here, where z here is treated to be a known or observed random variable conditioned upon all the unknown parameters, theta, mu, sigma, and pi for a mixture Gaussian model. And this is written by this is given by this equation over here, where we follow this Bayesian network such that the joint probability distribution of x and z is given by the probability of x conditioned upon z multiplied by the prior probability of z, following this Bayesian network here. And by putting in the definition of this to be a Gaussian mixture model and this to be a categorical distribution, we can obtain this particular equation here that represents the complete data log likelihood. And we can see that by this product terms over here, the log term can be pushed into the two product terms, and as a result this becomes two summation terms, where we'll bring the indices, the common indices here, down to this term here, and the log of the two product terms, the mixing coefficient and the normal distribution, would become a addition term here. And what's interesting here is that by doing this, because it's a complete log likelihood, the log term now appears inside the summations. And this we can switch the summation signs and look at just the points associated with the each component or respective component of the mixture Gaussian model. So this is the component, the kth component of the GMM, and this guy over here is each data point. So by switching this summation, we are looking at each one of the data point with respect to the kth component. But here we will still face one problem if we want to maximize this complete log likelihood, because in reality this z is not observed. This means that we cannot, we still have to solve for the known z in order for it to become this particular form here, such that the log will appear inside the summation term. And so instead of maximizing the joint log likelihood, we maximize its expectation under the latent variable distribution. So this means that instead of directly optimizing for this guy over here, because we do not know this z here is a latent random variable, we do not know it. So we'll maximize this unknown parameter over the expectation of this log likelihood, complete log likelihood, under the posterior distribution of the latent random variable. And by evaluating this guy over here, we'll get over the summation of all the z's, which we can rewritten into the summations over n which is the data point. So this is the n observed points, and then this guy over here, k, would be the components of each component of the GMM, kth component of the GMM. We can rewrite this posterior distribution and the complete log likelihood into this form over here, where this term here would simply becomes, applying a Bayes rule, this term here would simply becomes this term here, which is equivalent to our responsibility function that we have seen earlier on, because this is a function of all the O parameters initialized from the previous step. And now this would be multiplied by the complete log likelihood, and which we can rewrite into this form as we have derived earlier. So notice that the indices of z and k is not required here, because we are summing up over n and k, and all the terms that are appearing here inside here will take a z and k of 1. So this term can be omitted inside here. And now, having taken the expectation over the posterior distribution of z, we get this particular term over here, where the log term will still appear inside the summation term. And as well as now we do not have the problem of an unknown latent random variable of z, because this would be a fixed term, or we will know this term from the posterior distribution of z conditioned upon x and theta O here. So here we will solve the problem by optimizing this term over here, the expectation of the complete log likelihood over the posterior distribution, and under the we'll optimize this guy over here, max of this over the unknown parameter theta, and we won't have any problem anymore. And we'll see that this can be done in an alternating way, because we need to evaluate this responsibility function in the expectation step, and then we'll maximize over this term in the... Now, the last thing that we'll look at is the theory behind the EM algorithm and why it works. We have seen earlier that the maximization over the log likelihood is difficult due to the need of marginalization, the latent random variable, which appears inside the log term here. And we saw that it turns out that the maximization will be easier if we were to directly do a max of the unknown random variable with respect to the expectation of the posterior distribution of z conditioned upon x and the previous data, the unknown parameters, over the complete log likelihood of x and z conditioned upon theta. And we saw that in this case here, the log term will go inside the summation term, which becomes easier to solve in an alternating strategy. And it also turns out that the log likelihood can be maximized by maximizing the lower bound, which we denote by L of Q and theta within the EM algorithm. And we can start off by rewriting the log likelihood into the summation of a lower bound term, as well as the KL divergence term that is given by these two expressions over here. So the KL divergence terms is a way to measure the similarity of two distributions. Suppose that I'm looking at Q and a distribution of Q and a distribution of P. The KL divergence, which is strictly positive, will tell me how much Q and P, the two distributions, are similar to each other. So the less KL divergence, this means that if the KL divergence between Q and P is equals to 0, this means that the Q and P are the same distribution. And we'll look at this more about the definition of this more in the variational autoencoder, as well as the variational inference lecture coming in a few weeks' time. And this is formally, this is defined as the expectation of a distribution which we call Q, and the posterior distribution over Z in the EM algorithm. So now here, since the posterior distribution, we do not know this data here. Notice that this is not data O, this is the general unknown parameters which we don't know. This means that we do not know how to evaluate this particular function over here, or this probability distribution here. So we'll approximate it using some function or some probability distribution over Z. This means that we're going to use Q here as an approximation of the posterior distribution which we cannot evaluate in closed form. So here we'll simply minimize the KR divergence. This means that we want to minimize the difference between what we use to approximate the unknown posterior distribution, and using Q over here. So here we can show that the log likelihood is going to be the summation of this KR divergence and another term which we call the lower bound, which is evaluated to be this particular guy over here. It's an expectation over this approximated distribution and the log likelihood of the and the log of the division of the complete likelihood divided by this particular distribution that we are using to approximate the posterior distribution. We'll see a proof of this expression over here. So we'll start off with the lower bound and the KR divergence, which is given by these two terms over here that we have defined earlier. And then we can notice that we can factorize out the summation Z over Q of Z, since it appears in two terms, and then we can evaluate this log term to become log of the complete likelihood minus away log of Q, and this term here to be minus, so since there's a minus over here, minus log Z X theta. This is the posterior distribution of the latent random variable plus the division probability distribution here, so which is log Q. So applying the product rule, we can get from the joint distribution to these two terms over here. So this is just simply using the product rule, and then we can see that the log Q over here, it cancels out, as well as this particular term over here, the log Z, the posterior distribution over the latent random variable, it cancels out each other. So we are left with QZ multiplied by log of X conditional upon theta. And since this term here is independent of Z, we can pull it out of the summation sign, and the summation over Z on this proposal distribution Q over here is equals to 1, and therefore we ended up to be having the log likelihood distribution, which is what we have shown earlier in this in this expression over here. And the interesting thing is that by having this particular expression over here, we know that the log likelihood is equals to the lower bound plus a KL divergence term, which is strictly more than or equals to 0. So this term here is strictly more than or equals to 0. What it means is that we can actually look at it graphically, that the complete log likelihood is a sum of the lower bound plus the KL divergence here. And since we cannot optimize for this term directly over the unknown random variable, this means that we cannot do a argmax over theta over here, which proves to be very difficult because of the log term and the summation term. We can actually opt to do a easier optimization over the lower bound here. So what this means is that if we were to optimize this lower bound, we were to maximize this lower bound here over theta, and we will be pushing this guy up, we'll be pushing the blue line up, and since the KL divergence is more than or equals to 0, and it's also dependent on the unknown or the latent random variable Z, this means that by maximizing this guy, we will also be pushing this KLR divergence up, and hence we will be able to optimize for the log likelihood. So here we'll show that by maximizing the lower bound, it's equivalent to optimizing or maximizing the log likelihood. And we will see that we can maximize the lower bound by simply choosing this proposal distribution, which we denote as QZ, which I have mentioned earlier that we are using this to approximate the posterior distribution, the true posterior distribution of Z conditional upon X theta, where we do not know theta in this case here. So we can see that from the definition of the KR divergence here, we can minimize this KR divergence by turning this guy here to be 0, and hence this is equivalent to optimizing or maximizing for the lower bound. We'll push this all the way up, since the two terms must add up to be the log likelihoods. And we can see that this KR divergence term here can be minimized to 0, can be assigned to be 0 if we choose the proposal distribution here to be the posterior of Z conditional upon X theta O, where this term over here, the definition of the KL divergence is this given by this expression. So originally this guy here, it's QZ. So if we were to replace this with the posterior distribution of Z here, we can see that this term here becomes log of 1, and which is equivalent to 0. So this means that the whole thing here, the KL divergence term over here, will be 0. Hence, as a result, what we are doing here is that we are actually, by choosing Q to be taking this distribution over here that is dependent on the O parameters, we'll be maximizing this guy here. Since we are not changing the log likelihood in this case over here, we are simply replacing the latent random variables with the distribution of the latent random variables with the O parameters. So this means that the log likelihood here is not changed, but we are minimizing this guy here. What it means is that we are maximizing the lower bound such that it becomes equal to the log likelihood in this term here. And this is equivalent to the expectation under the latent variable distribution, where this particular lower bound that we have seen, that we have obtained from replacing this guy here, the Q of Z, with the posterior distribution of the under the O parameter distribution. The definition of this, which we have seen earlier, which is given by this expression over here. So now if we were to replace QZ with the O parameters, or the posterior distribution under the O parameters, this is what we are going to get, these terms over here that we are going to get. And we can see that the lower bound is the distribution of Q and theta, which is the parameters, the unknown parameters. We can see that this evaluates into two terms over here, where the first term, only the first term, is dependent on theta, whereas the other terms here, it's all dependent on theta O. Hence, this becomes a constant term. And we can see that the result is that this first term here is equivalent to the expected terms of Q that we have defined when we derive the EM algorithm. Now, in the next step, which is the maximization step, we can opt to do a maximization of this lower bound. So once we have chosen that the Q, the proposal distribution, is going to take the form of the posterior distribution of Z conditional upon theta O, the next thing that we see is that by choosing this, the lower bound becomes the expected value of the complete log likelihood over the latent distribution, over the posterior distribution of the latent random variable. And the next thing is that we have to find the new parameter by optimizing over, by maximizing this term over the theta, the unknown parameter. And we can see that by doing this, we'll be pushing this guy up. We'll be optimizing this guy by a certain gap over here, by a certain margin over here. And since we are having a new parameter here, this means that it will also affect the KL divergence, because this is also going to be affected, this is also going to be a function of the new parameter here. Hence, and what's interesting here is that the KL divergence is always more than or equals to 0. This means that after we have maximized this lower bound here by a certain margin, we push it up by a certain margin, the KR divergence will also at least be following this boundary over here. So it could be more than this because it's always more than or equals to 0, or it could also be at this lower bound here. Hence the term lower bound, because by maximizing this, we are guaranteed to have this margin of maximization and plus a certain gap over here that is provided for by the KL divergence. So what this means is that by iterating between the E and M steps, we are always trying to maximize this lower bound to such that we first minimize the KL divergence by choosing QZ to be equals to the posterior distribution of the latent random variable conditioned upon the O unknown parameter. And then maximizing this guy means that we are pushing the lower bound boundary, which is at least guaranteed to improve by a certain margin over here until convergence, as we have iterated between the expectation and maximization step. And an interesting thing here is that the expectation step is equivalent to computing the convex lower bound given the O parameters. This means that we are always guaranteed to find the minimal case over here, because in this case here, by choosing this, it has been proven here in this slide over here that by choosing the proposal distribution to take this form over here, we're always guaranteed to minimize this KL divergence, hence maximizing the lower bound here in this sense that we are going to get this lower bound to be equal to the log likelihood here. So this step is always guaranteed by this proof over here. Hence, it can be viewed as a convex lower bound. That means that we are always guaranteed to get a optimal solution for this particular expectation step. And then we maximize this lower bound to get the new parameters. So this can be viewed as a cost function. So let's view this the red curve here as our cost function, which is given by the log likelihood term here. So what it means here is that this is similar to the Gauss-Newton optimization, continuous optimization, where we are given some complicated function here, and in the Gauss-Newton step, we will compute the Hessian matrix, or in the Löwenberg-Marquardt step, we will compute J transpose J multiplied by delta x equals to negative of J transpose of the error term over here. So this J transpose J is equivalent, is a convex equation over here, is a convex cost function over here, where we can intuitively treat this as at the local operating point of this theta O here. We are actually computing, based on this operating point, a convex function which is illustrated as a quadratic function here, where there is a global optimal point here. So once we have evaluated this this quadratic function, which is equivalent to our lower bound here, we are guaranteed to find a global optima here. And the next step here would be to move to the theta nu over here by maximizing, based on this operating step over here, maximizing the term which is equivalent to this particular value over here, that we are going to find the theta nu by finding this global optimal point from the lower bound. And then once we are done with this, this is equivalent to the maximization step. We repeat the expectation maximization step, where we will give it a new estimate of the lower bound here based on this particular operating point, where this theta nu now becomes theta O, and we'll find the next theta nu here until we finally reach the global optima, and we will terminate. So what this means is that, or what this illustrated is that, the EM algorithm will always converge to a local minima. That means that regardless of how what your initialization is, the EM algorithm is always guaranteed to converge. However, it's not guaranteed that the EM algorithm will converge to a global optimal point, because you might have a very complicated log likelihood function that looks something like this, where there are many local minima and many local maximas. So suppose that this is my global optimal point, and if I were to start from here, for example, then by doing this EM algorithm, the expectation and maximization step, and what I will end up with would be this local minima point here. It will always guarantee to converge to some local minima, but this might not be my optimal solution or the global optimal solution. So this global optimality is not guaranteed by the EM algorithm, but convergence is always guaranteed. So in summary, we have looked at how to use the non-probabilistic k-mean algorithm to solve the clustering problem. We have also looked at the definition of the Gaussian mixture model. But it's important to note that the expectation maximization algorithm that we have derived need not necessarily be restricted to just the Gaussian mixture model. We have derived the general expectation maximization algorithm, and we saw how to apply this EM algorithm for the estimation of both the unknown parameters as well as the latent random variables. Thank you.